Now I'm going to be coding to solve for the temperature of our adiabatic flame. Just real quick, these top sections here refer to the GitHub page in which we can get a lot of our computational tools that we need for this coding assignment. And then from here we're importing a few different things. The .map is basically a storage method for variables, pandas, transforms our data, which will our results into just to make them better looking. JAX allows us to get a lot of our computational functions. Specifically, we need the JMP from JAX NumPy. Do a quick config update. This improves our precision. And then we needed to import the VSC, comp, and range functions, which are necessary for solving for temperature, and then the tools.che, which is basically a library of all the necessary information we need for our substances we're using in our chemical equation. So real quick, to reference that library to get the properties of the different chemicals we'll be using. Real quick, so we're going to be using oxygen as fuel, nitrogen, and this is basically just the air that reacts with the methane. We're producing carbon dioxide. And water. Shift enter. So now I'm going to just start with setting up our .map. So this one is going to hold all our known variables, or our constants that we already know. So first, original moles of methane, we're going to set as 1. And then we have our temperature, original temperature going in, which is going to be 298.15 degrees Kelvin, which is 25 degrees Celsius. And we have our O2 in excess, which we're told is 20%, which is 0.2 as a value. I did not mean that. Well, yeah, we'll come back to the .map for the range function once we set up our function. So to do that, we'll start off with our model. We're actually going to introduce another .map. Basically, what this whole model is doing is it's creating constraints for our answer. So we know a lot of small things about each individual variable, but when we put them all together and create a range, it helps constrain it, and we can accurately guess our temperature. So for our moles of O2 in, it's going to be hold on. I'm sorry. Set up another .map. Getting ahead of myself. .map. So it's our dot equal 2 times the initial methane times this is the excess O2. I'm just going to differentiate that real quick. Then we're going to have our moles of nitrogen gas, which is equal to O2 in. And then this is multiplied by the ratio of nitrogen to oxygen commonly found in air, since we're just burning it in open air. And that is a ratio of 79% nitrogen to around 21% oxygen. And then our moles of CO2 is going to be equal to moles of methane originally. And then our moles of O2 going out, and moles of O2 out is going to be equal to moles of O2 in. And then minus 2 times. And this all comes from our balanced chemical equation that Max balanced in the first video. And then our H2O, our water coming out. And that's going to be equal to 2 times moles of methane. And that's because for every 1 mole of methane put into the equation, you get 2 moles of water coming out. Okay. With space, we can begin to solve for the moles. Total moles coming in and out. And we're going to use some arrays from Jack's NumPy to help us with these. So number of moles in is equal to, and I'm going to do a JNP dot array. Okay. So we're going to have the moles of O2 in, moles of nitrogen. Originally, we have 0 moles of carbon dioxide. We have our methane. A strong suspicion that I've made a typo somewhere here. And we also have start with 0 moles of water. And then when we go down, it's saying that because I've yet to put the return. We're going to do our moles coming out of our function, which is also going to be an array. And our moles of O2 coming out. We have our nitrogen. We have our moles of CO2 coming out. All of our methane will be burned off, so that's going to be 0. And then we have our moles of water. Okay, and now we're going to do the enthalpy in and out. So we have our enthalpy in is going to be equal to, and we have our reference our chemi props or tools chemi to get our enthalpy values. So then that's going to be moles in temperature, which is going to be a range, which we have yet to put in, which it will be when we get to it. And then we should make sure that's correct, sorry. Temperature going in. We already have this one. Okay. And then our enthalpy out is going to be moles out and the temperature, which is what we're solving for. Then a return is going to be the number of moles coming in subtracted by number of moles coming out, or enthalpy in. Sorry, it's in enthalpy. Enthalpy in, enthalpy out. Minus R dot H out. R. Let me run that. Okay. So I am getting. Definitely have to put a colon right there. Again, R equals dot net. That should be right. Oh, indented, yeah. It's definitely supposed to be, yeah, indented a little bit. That's annoying. I'm surprised it didn't. No, just a tab. It's weird. I wonder if I clicked out of it. And, let me try that again. We're also getting more errors this time. Getting one of these. A lot of typos. It's very easy to make those mistakes with something like this. Looks like I'm good. Now I'm going to go back to this range that we have yet to create. So our temperature is going to be equal to a range. This helps constrain our values to more and allows us to accurately get our answer. So we have our initial guess is X. I'm just going to put that in as 1,000. We have our low. We'll start with our 298.5, and then our high 5,000. Should give us an accurate answer. Let me go ahead and run that. Run this. And now we should be able to use our VSC function. Solve. Let's see if that works. Nope. And that is because O2 in is not defined. Okay. Oh, that's because it should be r dot. Let me find where that is. It's in our r dot map. R dot. O2n. Guess I gotta run that again. Again. Once again. Attribute O2n. Did I make that same mistake? No. Put R2. Oh. I'm just gonna write it all. There definitely might be something earlier on that I forgot to change. Dot map has no attribute O2n. That's confusing. Everything should be correct. Oh, so capitals. Do a quick scan. Make sure everything else is capitalized. I've ran into this multiple times. When I've got everything capitalized, I definitely forget that a lot. I gotta run that again. Okay, there we go. So that is our intended result, and then by using our bsc.cdf run that, we should get a nice chart in which we have our temperature here about 2070 degrees Kelvin. So that is our desired result.